Hi everyone, welcome back. You are watching the sixth lecture of EE635 Applied Linear Algebra. My name is Debisattam and this happens to be the second module of the sixth lecture. Okay, so let's get back with what we were doing. For that, I would have to share my screen, which should be up any moment. Okay, here we are. Okay, so let me remind you about this table that we have formed. So the problem that we were trying to understand is this one, that suppose we have a matrix A. So let me write this as a recap, quick recap. Recall that A is a matrix of size m cross n. And suppose we have done a row operation on it. So MA is equal to A hat, where M is a square M cross M matrix. M is invertible. So every elementary row operation matrix is like that. Yeah. What we have found out is that here, if we look at column span of A, of course, row span remains invariant. So row span of A is the same as row span of A hat. No doubt about that. We have seen it before. Yeah. However, column span of A in general is not equal to column span of A. For specific cases, it may be true, but in general, it's not true. But the surprising part is that dimension of column span of A is equal to dimension of column span of A hat. The dimension remains invariant. And the reason for that was the claim, because if V1 dot 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 up to VR is a basis, oops, what am I writing? Is a basis for column span of A, then MV1 dot 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 up to MVR is a basis for column span of A hat, which is of course equal to column span of MA. This is what we have proven. And that is why we have got this one, because if this is a basis for column span of A, this is size R, this is going to be a basis for column span of A hat, and this also has size R. Therefore, the dimension of the column spans will remain the same. And that is why we have this table. So elementary row operation will keep the row span invariant. So therefore, row rank will also remain the same, which by the way is the dimension of the row span. Because the row span remains invariant, of course, the dimension is also going to remain invariant. Then surprisingly, although row operations, elementary row operations do not keep the column span invariant per se in general. However, it will keep the dimension of the column span invariant. So therefore, it keeps column rank invariant, which happens to be the dimension of the column span. And similarly, likewise for column operations will keep the row span in general changed. Yeah, but dimension of row span will not change. Therefore, row rank will remain the same, will remain invariant. Column span itself will remain invariant. So of course, the column rank will also remain invariant. Okay, so the crux of the matter finally is that elementary row operations as well as elementary column operations do not change the row rank nor the column rank. Yeah, so under elementary row operations and elementary column operations, both row rank and column rank will remain invariant. So this is our observation. Let me state this as a lemma. Let A be a matrix like this, then elementary row operations and elementary column operations keep row rank and column rank, row rank of A and column rank of A invariant. Yeah, lovely, no? But this has profound consequences. This lemma will prove that row rank is equal to column rank. You know why? Here it is. So theorem, I'm not going to give a formal proof of the theorem, which you will work out. We'll think about it and we'll work it out. I will just give you enough hints so that this should be obvious. Once again, A is a matrix of size m cross n. Then row rank of A is equal to column rank of A. How do we prove this? Notice. So we start with A and we do elementary row operations like we have done before. So these are all elementary row operations, And we continue doing this till we get to the matrix R. And this R happens to be the row reduced echelon form of A. Okay. Now, what do you remember about row reduced echelon form? Row reduced echelon form, this R is going to look like there will be zeros initially, then there will be a leading one appearing at the K1 position, and then there will be star, which stars are either zero or non-zero, like this. And then there will be once again zero, yeah, a leading one will appear. This will be the K2 position, and then there will be non-zero entries, zero non-zero entries. Yeah, like that. So this is how the elementary, this is how the row reduced echelon form is going to look like. The leading ones are going to appear at K1 position, K2 position, so on up to KR position with this one, which is at the KRth position. And then there will be all zero rows. Yeah. So these zero rows anyway don't do anything with the row span. So these zeros are there. But now, because we are allowed to do column operations, see what we can do. When we are doing column operations, notice that the columns where these leading ones appear, they have only this pivot entry, and every other entry is zero. Now think of this first leading one, which appears at the K1 column. Now using this guy, I can make every entry in the first row equal to zero by doing column operations without changing any other row, any other entries in any other rows. So using the leading one in row one, we can make every other entry in R1 equal to zero by elementary column operation without changing the other rows. Indeed, because when I'm doing elementary column operations with this column, yeah, because what will I be doing to create these zeros? Say I want to create this guy, this create a 0 here. I will multiply by this number, this column, and subtract from this column, right? So I will take this number, multiply here, and then subtract that multiple of that column from this column. Yeah, because these guys are all zeros, this 0 will appear everywhere here. No other rows will be changed, but this entry will be made 0. Similarly, I will make this entry 0 and so on, all the other entries 0 by using this leading 1 here by column operation. Yeah, without changing any other rows. Now, what can you say about the other leading ones? With the second leading one, I can make every other entry in row number 2 equal to 0, except that leading one. With the leading one in row number 3, I will make every other entry in row 3 0 without changing the other rows, right? So that way, by doing these column operations, by these elementary column operations, every entry other than the leading ones can be made 0. Yeah, and then that's not all. With column operations, now I'm allowed to permute the columns also, right? So if I permute the columns, then I can bring those columns in such a way that K1 appears at the 1 1 position. K1 is equal to 1, K2 is equal to 2, K3 is equal to 3, and so on up to Kr is equal to R, which means, and then by permutation, and then by permutation of rows, permutation of columns, we get finally, let me call it A hat. So because we have not used A hat here as yet, A hat, which is equal to, notice carefully, 1, 1, so on up to 1, yeah, 0, 0, and all big zeros here. Yeah, the short form of that is an R by R identity matrix, 0, 0, 0. Yeah, and notice, how did we get that A hat? This A hat was obtained from A by doing elementary row operations and elementary column operations. Yeah, which then by our earlier lemma, by this lemma would mean row rank. So this implies row rank of A is equal to row rank of A hat, and column rank of A is equal to column rank of A hat. Right? Now see, what is row rank of A hat? What is the dimension of this guy? This is the basis. How many such vectors are there? R vectors. This is R. So this row rank is R. This is in fact equal to the number of non-zero rows in the row reduced echelon form. Yeah, that is R. What is the column rank? Yeah, what is the dimension of the column span of this? Once again, R. So this is also R. So the two are equal. Therefore, row rank of A is equal to column rank of A, which is in fact equal to R. Great, no? Yeah. Yeah. Now on to the rank nullity theorem. So we understand rank now. So you can define it either as row rank or as column rank, doesn't matter because the two numbers are the same. So what is rank? Rank is the number, the dimension of the row span of A. That's in fact row rank, or the dimension of the column span of A, which is the column rank. But the two are equal, so it doesn't really matter. Yeah, so that's the rank. Now, secondly, what is nullity? So if you remember, we had defined this null space or the kernel of a matrix A. So once again, we have this matrix A, which is a matrix of size m cross n. Null space of A, or what we call the kernel of A, is defined as the collection of all those vectors in f to the n, so n tuples, such that Ax is equal to 0. That's the null space. Yeah, by nullity, we mean nullity is defined to be the dimension of kernel of A. Yeah, that's the nullity. Okay. What is rank nullity theorem? Rank nullity theorem says the following. So A is a matrix in F m cross n. Then rank nullity theorem says that dimension of kernel of A plus rank of A is equal to n, which is the dimension of the domain of domain of definition of A, the domain of. Yes, this should not come to you as a surprise, because once again, I'm not going to do the proof. I'm just going to give you enough hints. I'm going to give you a sketch of the proof. You can do the proof yourself. Okay, so so X belongs to a kernel of A if and only if Ax equal to 0. So then the kernel of A is nothing but the solution set of this set of system of homogeneous equations, right? And how have we characterized this system of homogeneous equations? The solution of this system of homogeneous equations? Look at the row reduced echelon form, yeah? And then divide the variables. So k1 up to kr. So xk1 up to xkr will be your dependent variables. All the other variables will be independent, right? And those independent variables, they are the free variables. Those variables can take any value. And we have seen before, you have done it yourself, in fact, as a homework problem, that in that case, you can write down all the solutions as a linear combination of some vectors, right? Those vectors which are obtained from the row reduced echelon form of A. Okay, so from so this is if and only if Rx is equal to 0, where R is the row reduced echelon form of the matrix A. But then this is nothing but xk1 equal to a linear combination of some C 1 I xi. I is in the gamma set. Xk2 is equal to summation I in gamma C2I xi. Remember? Yeah. So this, in fact, you can write as x1 up to xn. In that case, can be written as some. So these vectors xi's, if I define them as u, then u1 into a vector, say, what should I call it? Vector say v1 plus dot 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 up to u n minus r into vn minus r, where these vectors are such that you can show that. So this goes to you as homework. Show that v1 dot 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 up to vn minus r is a basis of kernel of A. Yeah, this V1 up to Vn minus R, these are vectors which are obtained from these parameters C1 to C1I for all i's in gamma, C2I for all i's in gamma. From there, you'll have to fish out this vector. It's kind of complicated to write this down in general, but if you look at examples, this will be absolutely clear to you. Okay, so therefore it follows that the dimension of the kernel of a matrix A is nothing but n minus R, where R is the number of non-zero rows in the RRE of A. Yeah, but that is the rank of A. That R is the rank of A. So then we have n minus R plus R is equal to n, and that is what the rank nullity theorem says. Okay. Now, if you think about the rank nullity theorem, it's in fact quite intuitive, you know. Let me stop sharing my screen. Yeah, so the rank nullity theorem is quite intuitive. What does it really say? So suppose we have a matrix of size 1 cross n. Yeah, so 1 cross n size matrix A, and A is equal to 0. I'm going to look at the null space of A. Okay, what would be the dimension? What would be its row reduced echelon form? Yeah, so you scan that, so it's a row now. A is just a row. So scan from the left. Whenever you find the first non-zero entry, divide by that entry, throughout the whole row, that will be its, the resulting row vector will be its row reduced echelon form. Yeah, so K1 will be some number. That will be the dependent variable, and every other variable will be independent. So you can choose any arbitrary value for those numbers. So that means, what is the degree of freedom here? What is the dimension of this null space? N minus 1. And it's very intuitive that it should be n minus 1. Of course, because see, I was in the whole n dimensional space, and then I have one equation that the x's have to satisfy. What would be the solution set? It would of course be a hyperplane of dimension n minus 1. So this equation will cut down the whole dimension by 1. In fact, we have seen this before. In R3, if you look at one equation, the solution of that is a plane, dimension 2. So one equation cuts down the dimension by 1. Geometrically, cutting down dimension by 1, I mean, one equation means what? There's this normal, and the solution is just the plane that is normal to that vector. So if it's n-dimensional space, if my ambient space is n-dimensional, then one equation will cut down the dimension by 1. Its orthogonal plane will have dimension n minus 1. If you have one more equation, which is, remember, independent of the original equation, then the dimension will be further cut down by 1. So now we'll have two non-parallel planes intersecting with each other. The dimension will be reduced further by 1. So if there are two independent equations, remember, independent equations, then the dimension of the solution space will be n minus 2. If they were dependent, then they are in fact the same equation, and therefore we'll have all the two equations, but the dimension will be just n minus 1, not n minus 2, because they are not independent. 3 independent equations, n minus 3. 4 independent equations, n minus 4. Not how many equations we had originally, but how many linearly independent equations we had. And that number, the number of linearly independent equations, yeah, comes from where? That's the dimension of the row span of the matrix A. That's the number of linearly independent rows, right? The maximum number of linearly independent rows. That's the dimension of the row span, and that is the rank of the matrix, or row rank, which is equal to column rank, of course. So rank gives us the number of linearly independent equations that we have. And rank nullity theorem says that the dimension of the null space. That is the dimension of the solution space of the homogeneous equations given by these rows. That dimension is equal to n, that is the dimension of the whole space, minus this number of linearly independent equations, which is equal to the rank. So nullity equals n minus rank. That's it. As simple as that. Okay. But in order to obtain this result, we had to go through a lot of calculations, as you have already seen. We had to first prove that row rank is equal to column rank. And then we have to use this idea of row reduced echelon form. Yeah, the fact that the the solution, the parameterized solution that you get from the row reduced echelon form actually gives you a basis for the solution space. All these things, all these extra informations we have to use. But if we allow ourselves the luxury of a little bit of abstraction, we will see that the calculations come down drastically, and one can prove rank nullity theorem independent of this row reduced echelon form, row rank, column rank, uh, elementary row operations, elementary column operations, all of that. Yeah, just by some abstract thinking, logical thinking, we'll be able to prove rank nullity theorem. And that is what we will see in the third and final module of this lecture. Okay, so see you on the other side of the break. Right, bye-bye.